Welcome back, everybody. The lecture today is about hypothesis testing for population percentages. We've spent the last couple lectures talking about hypothesis testing for population means, a different parameter. As we saw with confidence intervals, the shift from population means to population percentages is minor. It usually just involves changing the underlying probability distribution we use, as well as a couple of changes to the formulas. We're going to see the exact same thing with hypothesis testing. Our overall general process is going to be largely the same. The only difference is the probability distribution we end up using and some of the formulas that we end up using are going to be tweaked so that we're working with the appropriate parameter, in this case, a population percentage. You'll see this theme in general. Hypothesis testing, there are a lot of different types of hypothesis tests that you can do. We're going to cover one more next week, something called a two-sample t-test for differences in population means. In fact, even when we cover linear regression, we're going to talk about some of the hypothesis tests that Excel does in the background based on some of the parameters for that particular statistical setup. So hypothesis testing is a really big idea in inferential statistics. And hopefully what you'll see by looking at this population percentage example is that if you get the feel for how hypothesis testing works, the details can be kind of taken care of just by looking them up when you need it. But really understanding how and why a hypothesis test works is what will get you through a lot of different statistical techniques. So let's get started. The first thing that I want to point out is just like with our hypothesis testing for the means, the main goal is the same. We're going to start by making a claim about a population parameter. In this case, the parameter of interest we're going to focus on is a percentage. So we might make a claim about how many people in the US have blue eyes. And fundamentally what we want to do is answer the question, is this claim true or false? Our general approach is going to be using a simple random sample from the population. So we'll collect maybe 50 random people and we'll record, do they have blue eyes or something else? We're going to use the results of this simple random sample to try to provide evidence against the claim. So just like in our previous case, we're still playing the role of the prosecution. We're trying to prove that a null hypothesis or a claim about a population percentage is false. So let's jump over to our R visualization and take a look at how this might play out in terms of sampling distributions for these new parameters. Okay, here's a familiar simulator, but this time we're working with a percentage rather than a mean, so things have been kind of modified slightly. But the setup is more or less the same. What we're going to do here is compare an actual population, this is in our lower frame here in the muted colors, to a null population, which we get to control by setting our null hypothesis. So the actual population percentage, right, what's going on down here is 45%. I set that kind of separately. And what we're going to do is make a claim about what we believe the population percentage is going to be, right? In particular, we're interested in estimating the population of people who would say yes, which is blue in the null population and kind of this dark teal in the actual population. All right, so we get to set our own null hypothesis. In other words, we get to pick a claim that we're going to test. I'm going to try the following. Let's assume that our null hypothesis is that the percentage of people that will say yes in the population is equal to 64%. Now we know in reality, and this is information we don't normally have access to, but we know in reality that this null hypothesis is wrong because our actual population percentage here is 45%. So how does a hypothesis test work? Well, essentially what happens is we drop over to looking at what would happen if we sampled from our null population. So let's assume the null hypothesis is true, and let's think about what the sampling distribution for sample percentages would be. In other words, as I take random samples, so you'll notice each time I hit get one sample, a new collection of dots from this null population is selected, and what we're recording down here in this histogram is the percentage for each sample of blue out of the total. All right, so when I click a new sample, I count up how many total blue dots were circled, and I divide it by my sample size 85. So the sampling distribution, we can get a PCAT by just doing this a couple thousand times. It'll give us a pretty good sense of what the sampling distribution for this sample percentage is. Now, we're obviously not going to do it 1,000 times, but maybe I'll do it about 1,000 times just to make sure we're getting a nice consistent picture. One important thing to notice here is that this has a nice bell-shaped curve to it, okay? So in other words, this is starting to have either a t or a normal distribution, and we'll clear that up in a second. And by looking at this, what we get to say is that assuming the null hypothesis is true, right? Assuming that we sampled from the null distribution, right? Or sorry, from the null population where 64% of the population would say yes, right? Our most likely percentages are kind of sitting up here in this region here, around 60, right? The peak is probably right around 64, and we drop off quickly heading down to 50% or past 75%. So these are the most likely sample percentages that we would get in this range here, assuming that the null hypothesis is true. Now, if you had access to the actual population, you could compute its sampling distribution for the sample percentage, and we would compare the two. So let's do that. We can show the actual population sampling distribution, and you can see that they're quite different. In this kind of muted color, this is what the sampling distribution would be from selecting from the actual population. And you can see that the most likely scores are more down here in the 0.45, 0.46 range. And we can kind of play with the bins to sort of discover that this thing has a very nice normal distribution. Here's a perfect picture, right? Good number of bins. You can see that the most likely sample percentages we would get out of the actual population are in this 0.45, 0.5 region, and then they taper off quickly as you head in either direction. Contrast that against the sampling distribution you would get if we assume the null hypothesis is true, and we're in a much higher range of sample percentages that we'll get back. So since these two things don't agree, what we're going to see is that if we play devil's advocate and assume that the null hypothesis is true, most likely when we go out and collect actual data, we're going to get a sample percentage out in this range, and the disparity between the sample percentage we see from our data and what we expect to see from the null distribution are very different. And in that case, we'll say we've provided evidence against the null hypothesis. But fundamentally, it comes down to different sampling distributions between the actual population and the one that should occur if you assume your null hypothesis is correct. So this is how our hypothesis test is working. Very similar to the sample means, except now we're looking at a distribution for sample percentages instead. This will have its own probability distribution, and that's what we're going to use to compute p-values as we've done in other cases. There are a couple of key takeaways that we get from this visualization that we just saw. First of all, notice that the sampling distribution of p hat, whether we were doing the actual distribution or the null distribution, the sampling distribution ended up having a nice bell-shaped curve. Now in the video, in the visualization, I said that could be either the t or the z distribution. It turns out the normal distribution is the best estimator for this. So we're going to be using the standard normal distribution when we talk about a probability model. Okay, so a good thing to keep in mind, whenever you're doing hypothesis tests or confidence intervals for means, you use the t-distribution. Whenever it's a hypothesis test or confidence interval for population proportions, you're going to use the normal distribution or the standard normal distribution. The second thing that we notice is that if the null hypothesis is wrong, as it was in our visualization, we're likely to collect a sample p-hat, right? Something from the actual population that's very different from the proposed population percentage. In other words, what we see in our data is going to be very different from what we propose in our null hypothesis. And essentially the way that we provide evidence against the null hypothesis is we hope to collect data that has extreme values for this p-hat, for this sample percentage. And if they're extreme, that's going to provide evidence against the null hypothesis. And fundamentally, we measure how extreme it is, right? Are we proving that the null hypothesis is false beyond a reasonable doubt? We measure how extreme a sample percentage is by computing a p-value. And this is exactly what we did when we were doing hypothesis testing for means. So let's jump to our general process. The first thing we're going to do is take a claim about a population percentage, and we're going to write it out in terms of the null and alternative hypotheses for our situation, for the claim that we're testing. We'll determine the type of test. From the sample percentage, which we can compute from our data, we're going to compute a z-score version of the sample percentage we actually observed. And it's going to use a different formula. Again, this is on our exam, so we don't have to worry about memorizing it, but we do need to know the terms inside of it. P hat is our sample percentage. P without the hat is our population proportion that's proposed inside of our null hypothesis. So this is what we see in our data. This is what we're testing in our claim. So we'll compute a test statistic, which we'll call z hat, which is telling us that we should be using our normal distribution, our standard normal distribution, to work with it. Once we have a test statistic, a z-score version of the sample data we're working with, we're going to compute a p-value and then base our results on whether that p-value is below a certain significance level.